Okay, what if I told you that there's a single, simple rule that pretty much explains all of physics? I'm talking everything, from a planet orbiting the sun to the super weird world of quantum mechanics. Everything we know could come from just one core idea. It sounds kind of like science fiction, right? But it's actually at the very heart of modern physics. So, let's dive in and see how we found it.
And no, I'm not exaggerating here. We're talking about a concept so powerful that it can take the place of classical mechanics, electromagnetism, all the way down to how the tiniest fundamental particles behave. I mean, it's a huge, huge idea.
All right, so what is this thing, this ultimate law? To figure it out, we're not going to start with, black holes or the Big Bang. Nope. Our journey actually starts with a surprisingly practical puzzle, something that stumped the greatest minds way back in the 17th century.
Yeah, a rule for everything. And believe it or not, the whole quest to find it started with one little question. What's the fastest way to get from here to there?
Okay, picture this. You've got a ball. You've got point A up high and point B down low. You want that ball to slide from A to B as fast as humanly possible. What shape do you make the ramp? That's the question. It's famously called the problem of fastest descent.
And look, this wasn't some friendly little brain teaser, oh no. This became a formal challenge, basically a mathematical duel for the smartest people alive at the time.
Now your brain, my brain, everyone's brain immediately goes, a straight line, duh, it's the shortest distance. But that's wrong. To get there the fastest, you actually need to build up speed right at the beginning. So a curve that dips down really steeply at the start is going to be better. Even though it's a longer path, that initial burst of speed makes all the difference. The real question is, what's the perfect curve?
So Galileo had a crack at it and thought, maybe it's the arc of a circle? Nope, he was wrong. Then, in 1696, this brilliant but kinda arrogant mathematician, Johann Bernoulli, decides to make it a public challenge, to flex a little. Well, the problem makes its way to Isaac Newton. And Newton, supposedly super annoyed to even be bothered with it, just sits down and solves it. In one night. A problem that took Bernoulli himself 2 weeks to figure out.
And get this, Newton sent in his answer completely anonymously. But it didn't matter. When Bernoulli saw the solution, he famously said, "I recognize the lion by his claw." He knew. He just knew there was only one person on the planet who could have come up with something that good.
But here's where the story gets really interesting. Newton's solution was, pure genius. But Bernoulli's own solution? It was maybe even more creative. Because he didn't solve it using the physics of falling objects, he solved it by looking at something totally different, light.
The key for Bernoulli was this idea called Fermat's principle. And it's pretty simple. Light doesn't always take the shortest path, but it always takes the fastest one. It's the reason light bounces off a mirror at the same angle it hits it, and it's why a straw looks bent in a glass of water. It seems like nature itself is obsessed with saving time.
And this was Bernoulli's big aha moment. He just decided to pretend the falling ball was actually a ray of light. And he imagined this light traveling through different layers, kind of like air and water, that would make it speed up and bend, just like gravity makes the ball speed up. Once he reframed the problem like that, he could use Fermat's principle of least time to find the exact path. Brilliant.
So what was the answer? Not a circle, but a curve called a cycloid. It's the path you'd get if you tracked a point on the edge of a rolling wheel. And Bernoulli must have had his mind blown because he realized he'd just shown that the math for falling objects and the math for light were kind of the same. There was some deeper connection there.
And that little discovery, that was just the tip of the iceberg. It got people thinking, okay, so light takes the path of least time. Could it be that everything in nature follows some kind of least something rule?
So flash forward to the 1740s. A physicist named Maupertuis comes along and proposes this new thing he calls action. For him, it was basically mass times velocity times distance. And he made this wild claim. He said that nature always chooses the path that minimizes this action. It was a really cool idea, but at first, everyone pretty much laughed at him.
See, Maupertuis's idea was a bit fuzzy on the math, but the great Leonhard Euler saw something in it. He took the idea, tightened it up, added some important rules like conservation of energy, and then, finally, another genius, Joseph Louis Lagrange, came along and gave it a solid universal proof. He turned it from a quirky idea into real hardcore physics.
Today, we have a more modern version, usually called Hamilton's principle, and it's all about energy. The action is now defined as the kinetic energy minus the potential energy, all added up over the entire path.
The principle says that nature will always choose a path where that value is stationary. We'll get to what that means in a sec. But the crazy part is, when you do all the math, this fancy new principle gives you the exact same results as Newton's good old F equals ma.
Okay, so if it's just a super complicated way of saying F equals ma, why on earth should we care? Well, because this new way of looking at things, it's a game changer.
Yeah, I mean, that really is the million-dollar question, right? F equals ma is simple. You can write it on a t-shirt. Why would we ever trade that for something called the principle of least action?
Because the difference is huge. Think about it. Newton's physics is all about forces, pushes, pulls, things that have a direction. You have to keep track of all these arrows, and it can get really complicated fast. But this new approach, Lagrangian physics, it doesn't care about forces. It only cares about energy, kinetic and potential energy. And energy is just a number. It doesn't have a direction. This simple switch from arrows to numbers creates a kind of problem-solving machine.
And the benefits are massive. Suddenly, you can handle really complex systems much more easily. It doesn't matter what coordinate system you use, it just works. And it almost always gives you the answer in a cleaner, more elegant way. Take the double pendulum. You know, one pendulum hanging off another one. Trying to solve that with F equals ma is an absolute nightmare. With this energy method, it's still hard, but it's totally manageable.
Okay, just one little technical point to be super accurate. We've been calling it least action, but really it should be called stationary action. Here's why. Imagine a ball on a bumpy landscape. It's going to roll down and settle at the bottom of a valley, right? That's a minimum. But it could also, in theory, be perfectly balanced on the very top of a hill. That's a maximum. At both the bottom of the valley and the top of the hill, the ground is flat. It's stationary. Nature just looks for one of those flat spots. Most of the time it's a minimum, but not always.
And this is where it gets truly wild. This whole idea, which started with a ball rolling down a ramp, it turns out to be one of the absolute cornerstones of quantum mechanics. So you have to ask yourself, is that just a fluke, a weird mathematical coincidence, or is this principle hinting at something incredibly deep about the universe itself? That maybe, just maybe, the fundamental rule of reality is simply to find the most efficient way to get things done.